Well, hi everybody and welcome to my channel Art and Physics. Well, in this video we will continue with the analysis of mechanical system using Lagrangian dynamics, but here we will also use modal analysis in order to find out the mode shapes and frequencies of vibration of the mechanical system, and also we will use a technique called static condensation that allow us to eliminate those coordinates with no mass attached to it. So let's first begin by explaining the mechanical system. Is depicted here on the screen. Is basically formed by three objects. The first object is a mass, a cart that can move horizontally and is connected to a fixed point by means of a spring of a stiffness K. Second springs connect this mass, this cart, with one of the extreme of a bar. This bar can rotate through point O, and also, very important, this is a massless bar. We will assume that the mass of this bar is very small. This is practically zero. This will be important later. In the opposite extreme of this bar, a third spring connects the center of a cylinder that rolls without slipping on a horizontal surface. And finally, a fourth spring of stiffness 3/2K connect this cylinder to a fixed point. So first we will choose our coordinates, the coordinates in order to describe the motion of the system. Let's first call x the coordinate that describe the horizontal displacement of this cart. The second coordinate that we will use will be the angle of rotation of the cylinder. I will call it theta sub 1. Let's remember that this cylinder can be described either using the horizontal displacement of the center of mass of the cylinder or the angle of rotation. Both of these coordinates are related. Okay, so we can choose whatever of the two of us we want. In this case, I will use theta sub 1. And a third coordinate is also another angle of rotation. I will call it theta sub 2, that describes the rotation of this bar to the point O. So with these three coordinates, we can write the Lagrangian. The Lagrangian, remember, is equal to the kinetic energy of the system minus its potential energy. So first, let's write here the kinetic energy. The kinetic energy in this case is formed first by the translational kinetic energy of the cart, which is simply 1.5 m times x dot square, and the kinetic energy of the cylinder. There's two ways to write this kinetic energy. I will write it here as follows. First, I write the translational kinetic energy of the cylinder, and then I will add the rotational kinetic energy. The translational kinetic energy is simply 1/2 over 1/2 times m times the translational velocity, which in this case is equal to r theta 1 dot square, plus the rotational kinetic energy is equal to 1/2 the inertia of the cylinder, which in turn is 1/2 times m times r square, and multiply by the rotational angular velocity theta 1 here, theta 1 dot square. So this whole expression is the kinetic energy of the system. This can be simplified as follows. This sum here can be written as 3/4 m r squared theta 1 dot square. This same result can be obtained if we remember that the instantaneous center of rotation of this cylinder is located precisely at the point on which the cylinder touches the horizontal surface. So here there is the kinetic energy. Let's continue now with the potential energy, B. In this case, the potential energy came from the elastic potential energy stored by this spring. And the first spring is fairly easy. It's just 1/2 times k times x squared, x being the deformation of this spring. For the second spring, we should here emphasize that we will interested on the small oscillation of the system. If we analyze the small oscillation, then the deformation of this spring is equal to x plus the horizontal displacement of the upper extreme of this bar, which in our case is equal to r times theta 2. So this is the formation of the second spring. For the third spring, it's very similar. Remember that the stiffness in this case is 3.5 K, and the deformation can also be written in the case of a small oscillation as in this case 2r theta 2 plus r theta 1. R theta 1 is the horizontal displacement of the center of these cylinders. And finally, for the fourth spring is 1/2 times 3/2K times, well, in this case, this spring will be elongated exactly the same distance at this distance as the motion of the displacement of the center of the cylinder, which is in our case r theta 1. So this will be r squared theta 1 squared. There it is, the potential energy of the system. Now we can simplify this whole expression. If we do the respective simplification, we obtain the following result: k times x squared plus 3/2 k r squared theta 1 squared plus 7/2 k r squared theta dot square, and finally plus k theta 2 r times x plus 3r theta 1. Well, this is just simply the result if we simplify and do the corresponding algebraic operation on the expression for the potential energy. Okay. Now we have to remember that the Lagrangian is equal to the kinetic energy. I will emphasize here, this is the kinetic energy, and our potential energy, I will use this square rectangle. Okay, so now we can write the equations of motion using Lagrangian dynamics. And let's first calculate the corresponding partial derivatives. For the first coordinate, we need to find the partial derivative of the Lagrangian with respect to x dot. Well, in our case, it is very simple. This is just m times x dot. The only equation, the only x dot only appears on the kinetic energy. Okay, it cannot appear on the potential energy. Let's remember the potential energy only depends on the position of the coordinate, not in the velocities. So from here, the total derivative of this later partial derivative with respect to time is just simply m times x double dot. Okay, and the partial derivative of the Lagrangian with respect to x, in our case where x appears in the potential energy in this term. If we apply this derivative, we can conclude that this is minus minus 2 kx minus k theta 2 r. Don't forget, the minus here is because the Lagrangian is equal to kinetic energy minus potential energy. And finally, we can set up our first equation of motion. Is in this case is this total derivative with respect to time, and m times x double dot minus this other derivative. There's a lot of minus here that will cancel each other. 2 times x plus k to r. In this case, equal to 0, but because there are no non-conservative forces acting in our system. So that's the first of the three equations. The second one corresponds to the coordinate theta 1. So again, I will calculate this partial derivative. In our case, if we analyze the expression of the kinetic and potential, well, again, the theta 1 dot only appears in the expression for the kinetic energy, and the result is here 3.5 m r square theta 1 dot, which implies that this total derivative with respect to the time of this later partial derivative is just simply 3/2 m r squared theta 1 double dot. And finally, the derivative of the Lagrangian with respect to theta 1 is in our case minus 3k r squared theta 1 minus again 3k r squared theta 2, which implies that the second equation of motion of our mechanical system is 3/2 m r squared theta 1 double dot plus 3k r squared theta 1 plus 3k r squared theta 2. Okay, and finally our third equation, which is related to the coordinate theta 2. This partial derivative, well, if we look again closely to the expression of the kinetic and potential energy, we realize that the term theta 2 dot doesn't appear in any of this expression, and that's something that we can expect because theta 2 denotes the rotation of the bar, and this is a massless bar. Let's emphasize this. This is a massless, okay, massless bar. We are assuming there is no or physical object have mass, but in this case we are assuming that it's very small, so in practice it's zero. And then the expression of the kinetic energy doesn't contain theta 2 dot. No, this is simply zero. Okay, but the partial derivative of the Lagrangian with respect to theta 2 in our case is equal to 7 k r squared theta 2 plus k r x plus 3r theta 1. Okay, and so basically this third equation of motion can be written as follows. So there we have it. I will also use, in this case, a blue rectangle in order to emphasize these equations, these results, our three equations of motion. Okay, there is the first one. Well, these three equations of motion can be written in matrix form. It's more adequate to do so. So if we use a matrix formulation, this equation of motion can be written as follows in the matrix form. These three equations can be written in a compact form as the following. L is this vector, x 2 dot theta 1 2 dot theta 2 double dot plus this matrix multiplied by this vector, all is equal in our case to this zero vector here. I will also use this in order to emphasize these submatrices. Okay, So there is the three equations of motion of our system written in matrix form. So what happened here? If we want to do the modal analysis for this system, we will have a slight little problem, because this first matrix, we can think in this as the mass matrix of our system. That's effectively that it is our mass matrix, as a zero in this diagonal term. That's a problem. This second matrix here can be thought as our stiffness matrix. There's a mass matrix and a stiffness matrix. So we need to find a way in which we can eliminate this θ2 coordinate for our analysis, because the problem is that it's a zero contained in this diagonal of this matrix. We can do this as following, and let's first think in the general case. This is like a little parenthesis here. If we think the general case, so let's suppose that we have a system in which the coordinates can be divided in two sets. A first set of coordinates relate to all of those coordinates with mass associated to it. I will call it in the case just simply u. In our case, in our system, this vector u will be x and θ1. And a second set of coordinates, I will call it u sub 0, are all of those coordinates with no mass associated to it. So in general, we can write this system as follows. I will use this notation in order to emphasize that these are metrics plus, in our general case, a matrix that can be written in the following way. I will write it first. This will be equal to 0. What we are saying here is, again, we are dividing the total set of coordinates of our system in two groups. The first group, u, is has all of the coordinates with mass associated to it, and u sub 0 all the coordinates with no mass associated to it. So we will have it. The mass matrix will have terms m associated with u, but 0 associated with u sub 0, and this will be the submatrices of the stiffness matrix. This system then can be written, can be solved in the following way. The first will be m times u double dot plus k u times u plus k u sub 0 times u sub 0 equals 0, and the second will be k u 0 transpose times u plus k u 0 times u 0 equal 0. From the second of this equation, we can conclude that u0 is equal to minus k u0 inverse times k u0 transpose times u. This is the conclusion that we can obtain from this second equation here. If we eliminate u0 from this second equation, we reach to this result. We can then plug this result on the first of our equations, and then this equation can be written as the following way. And reach this equation here. That is very important. I will also use a blue rectangle here to emphasize this important result. So what we have done here, we have break this equation of motion, eliminating all of those coordinates with no mass associated to it. In other words, the coordinate u0 doesn't appear in this equation. This equation can be then can be then understood as simply m times u double dot plus I will call k star u equal 0, from which it should be clear that this k star is equal to all of this term here in the parentheses. So we can, using this procedure, that it's called a static condensation, we can eliminate again those coordinates with no mass associated to it. Then, if we came back to our original problem, we can then identify these different submatrix of the stiffness matrix. If we remember, our stiffness matrix is up here. This is our stiffness matrix. If we then identify the different terms, this let's call it this KUU is all of this. This KUU0 is this one. This is the transpose, and this KU0U0. But in our case, it's just simply a scalar on a matrix of one by one. So we can identify this respective term. KU is equal to, I will write it here again, 2K00 3KR squared. KU U0 is actually a vector, KR 3KR squared, and KU0 U sub 0 is a scalar, 7KR squared. If we calculate then K star using this expression here, though all of this term on this parenthesis, it's a slightly mistake here. Sorry, I should not breathe here the term u. That's why I factorize u. Sorry there. That it is. This is the expression for K star. Sorry. If we calculate all this term, we conclude that our matrix K star can be written as the following. I will let you do as an exercise of matrix algebra. Okay, and then our new equation of motion with only the coordinate with mass associated to it can be written as the following way. This time M mass matrix plus our K star stiffness matrix. There it is. It's our system reduced to only those, let's call it dynamic coordinates. Okay, from here, so we can find the mode shapes and the respective frequencies of oscillation simply by solving the problem of eigenvectors and eigenvalues of this system of equations. We will remember that in order to do so, we have to calculate the determinant of the stiffness matrix, this K star, minus the mass matrix times omega squared, where omega is the frequency of oscillation. In other words, we have to find this determinant and set it up to 0. This should be 0. So, well, the classic determinant, this diagonal here, I will multiply this term by this term minus the product of this one and this one, set it to 0. We will find then the characteristic equation. There's some algebraic operation that need to be done here. I will let it to you in order to practice and complete the result. But if you do this calculation, you should reach to the following characteristic equation, which is m squared omega to the 4 minus 3k m omega squared plus 2k squared equals 0. And this equation here is a b-quadratic equation on omega that can be solved as a traditional and common second-degree equation. The solution here is equal omega. I will use the classic expression formula for the second-degree equation is 3km plus minus, well, here in the determinant will be equal to 9k squared m squared minus 8k squared m squared. Well, this is just 1k squared m squared. I will let it here. And we conclude that the two frequencies of oscillation are equal to, first, square root of 2 times big omega. I will immediately, where this big omega is just the square root of k over m. In other words, this big omega is really actually the frequency of oscillation of 1 degree of freedom oscillation with mass m and stiffness k. These are then the two frequencies of oscillation of our system. The mode shapes can be obtained replacing plugging this respective omega square on this matrix here, and then calculated the respective coordinates. This is a fairly very straightforward exercise. I will just write here the results. The result then for these two mode shapes are, for the first mode, equal to 1 and minus 1 over 3r, and the second mode is 1 and 2 over r. Okay, so that's it. There's a lot of some algebraic operation that I will let up to you to complete. I recommend you to do this exercise. This kind of work is good in order to practice. But the general structure of the resolution of this kind of problem is described in this video. This is then the problem that we solve using, again, first Lagrangian dynamics, then and modal analysis and static condensation. That this method that we use in order to write the equation of motion of the system only in terms of the dynamic coordinates, so all of these coordinates that has mass associated to it. So thank you very much for seeing this video. If you have any comments, let me know in the comment section. Give it a like, and if you like this kind of problems on physics, you can subscribe to my channel. So bye bye. Let's see you in the next video.